before, it's called a heating curve of a substance. So if we start with a single substance and we consistently add heat to it and we record the temperatures, we'll end up with a graph that looks something like this, which is known as a heating curve. And we end up with these 5 different segments. So notice the y-axis is known at, or is labeled as temperature in Celsius. So I'm just going to assign temperature values, just increasing by tens, just to give an idea. I know that this is not perfect, but it will just help us think through the process a little bit. Okay, so each segment describes what is going on with an energy transfer and how it affects the sample. So the segment AB, notice it's at the lowest temperature range compared to any of the other samples. A extends from a temperature of 10 to just under 40, and then CD starts at that just under 40 temperature, and it climbs all the way up to around 80 according to my scaling. DE holds a temperature of around 80, and then segment EF, it starts at 80 and it climbs up to close to 120. So since segment AB exists in the lowest temperature range compared to all of the other segments, it represents when our sample is completely in the solid phase. Because the solid state of a sample always exists at a lower temperature than its liquid or gaseous phase. So I always like to draw those particle diagrams. Whereas segment EF is the complete opposite. This is the segment that is at the highest temperature range, and the phase of matter that tends to require a higher temperature to be present would be the vapor or gas phase. And then segment CD, it's in the middle. It's higher, it's at a higher temperature range than the solid, but lower temperature range than the gas. So this would be when our sample is in the liquid phase. So the particles touch and are disorganized. So notice then we have segment BC. BC is sandwiched between the solid and the liquid, and it connects the two different phase segments. It connects the solid to the liquid. So that represents the idea that our sample can go through a phase change. So if we start off as a solid, the solid can melt into a liquid. But if we start off as a liquid, it can phase change to become a solid. So we see the cycling or both phases present here. We see a similar trend with segment DE, which is sandwiched between the liquid phase and the gaseous phase. It links those two segments together. So here we have a place that represents another phase change, but this time it's phase changing between liquid and gas. So if our sample starts off as a liquid, it can boil or vaporize to become a gas. But if we start off as a gas, it can go through a phase change and become and reform or condense as a liquid. Now, if we follow segment BC all the way back to that y-axis and we read this temperature off of the y-axis, the place of phase change, wherever segment BC strikes the y-axis, because this is the phase where a solid melts or a liquid freezes, that temperature would be referred to as the substance's melting point and freezing point, because this is the phase change. The solid melts, the liquid freezes. So melting and freezing occur at the same temperature. So if we did the same thing for segment DE, and we follow it all the way back to where it strikes that y-axis, it's the place of phase change where a liquid boils into a gas, so we could call this the boiling point, or the gas condenses back into the liquid, so we could also call it the condensing point. Now we need to do some labeling with these segments. So I hope you notice that when you look at segment A, you see that it starts at one temperature and the segment ends at a different temperature. So segment A shows a change in the temperature, a delta T. But segment BC, it starts at this temperature is just a little under 40 and it ends at that same temperature. So segment BC, there is no delta T occurring. The temperature is constant. So what does this tell us about energy? Well, with energy, we have two characteristics. So energy has two characteristics. So energy can be described as being kinetic, in which it's being used and there's movement. So I'm going to write used, movement, or potential, which means it is being stored. So on this diagram, the heating curve of the sample, each segment represents what's going on with those two different characteristics. So temperature, we learn to associate it with the average kinetic energy, the average movement of the particles. So if you have a change in the temperature, then there is going to be a change in the average movement of all the particles. So we have a change in the kinetic energy, trying to write KE there. So wherever there's a delta T occurring, we understand there's a change in the kinetic nature of the sample. So we see a change or in the ability to move. So we see a delta in the movement. So either the particles are able to start to move more or they move less. In the areas where there's no delta T, okay, that means a different characteristic of energy is being affected here. I guess I'll go with blue here. So when there's no change in the temperature is remaining constant, so the amount of movement that the particles displayed remains the same. They just keep moving at that same speed or with that same ability. So what this means is, but there's still energy transfer going on here. So this means that there's a change in the potential energy. The amount of stored energy is changing. Stored energy is increasing versus going B or C back to B. Stored energy is decreasing. So here's the thing. I like to think about the stored energy as like when I eat too much food and my body stores it. And if I store way too much energy, I get a little bit bigger, right? So as you change the amount of potential energy, think about that energy. It's either pushing the particles away from each other or pulling them closer together. So when you change the amount of potential energy, you change the attraction strength between the molecules. So either the molecules, the attraction strength have decreased and they're allowed to spread out because there's too much stored energy, or the stored energy has decreased, the particles have moved closer together because they're able to move in closer and their attraction strength increases. So we can go ahead and label. So either a segment represents a change in the kinetic nature or the potential nature. So C to D, since we start at one temperature and end at a different one, there's a delta T, so we see a change in the kinetic nature and the molecule's ability to move. we see the same thing with segment E to F, because it starts at one temperature and the segment ends at a different one. So once again, there is a delta T. So we are seeing a change in the kinetic nature. But when we look at segment D to E, we see the temperature starts and ends at the same value. So there is no delta T. The temperature is constant. So when there's no delta T, that means that we see a change in the potential or stored amount of energy, and that amount of change either allows them, pushes the particles farther from each other and attractions weaken, or they move closer together and the attraction strengthens. So when we change the potential energy, we change the attraction between the molecules. One last note here, that when we look at this diagram holistically from point A to point F, so we just look at it from the beginning to the end, so we look at it in this direction. So overall, to get from point A to point F, we see that we start at a temperature around 10 and we're ending at a temperature around 120. Well, the only way you're going to get the sample's temperature to increase from 10 to 120 degrees Celsius is if energy goes into or enters the sample. So energy enters our sample. And if energy enters our sample, that means it's an endothermic process. So here we go. And because it's an endothermic process, for A to climb up to B's temperature, for C to climb up to D's temperature, for E to climb up to F's temperature, that means that overall, our sample, our particles, have an increase in the kinetic energy. So there's an increase in the kinetic energy. And then from our particles to go from touching in complete order to, well, touching but no order, ability to move around, to no touching, no order, do whatever they want, that means that there's also an increase in the potential energy.